In this question, the position vector of a particle relative to a fixed point, the origin at time t, is given by this entire expression, and we are supposed to find the velocity vector. How do we find velocity from the position vector? We use differentiation. Velocity vector v will have two components, the x component as well as the y component. To find the x component of velocity, we will differentiate the x component of position vector with respect to time. So going back to the OP vector, which is our R vector, the position vector. In this position vector, the x component is sine t squared. So we have to differentiate this with respect to time. So Vx will be written as the derivative of sine t squared with respect to time. The derivative of sine is cos, so we'll get cos t squared, and we are using the chain rule, so we differentiate the t square which is in the bracket, which we'll get as 2t. Hence, Vx will be 2t into cos t square. That's the expression for Vx. Let us find out Vy by differentiating the y component with respect to time. Now, the y component is cos t square. So let's write down d by dt of cos t square. Now, the derivative of cos is negative sign. So we'll write negative sine t square, and using the chain rule, 2t. Hence, we will write Vy is equal to negative 2t sine t square. Now, let us write down the final velocity vector. So, we'll write V vector is equal to 2t cos t square is the x component, and minus 2t sine t squared as the y component. And that's the answer for part A. In the part B, we have to show that the acceleration vector of P is never parallel to the position vector of P. Now, before we can do that, we have to first find out the acceleration vector. And how do we do that? We differentiate velocity with respect to time. So initially, we had differentiated the position vector with respect to time to get the velocity vector. And then we'll differentiate the velocity vector one more time with respect to time to get the acceleration vector. So velocity vector has two components, Vx and Vy. To get the x component of acceleration, we will differentiate Vx with respect to time. So let's write down d by dt of 2t cos t square. Now here we have two functions, t and the cos function. So we will use the product rule. 2 in this expression is a constant that can be taken out of the derivative. So let's write down 2 multiplied by the first function into the derivative of the second function. T is the first function here. So we'll write t multiplied by the derivative of cos t square, which will be negative sine t square multiplied by 2t, plus the second function into the derivative of the first function. First function is t, the derivative of t is 1. So in the bracket, we will get 2t square with a minus sign and sine t square plus cos t square. This is the x component of acceleration. Similarly, let us identify the y component of acceleration, which will be d by dt of Vy. And Vy we had found out earlier as negative 2t sine t square. So let us write down d by dt of negative 2t sine t squared. Minus 2 is a constant that will be taken out of the integration, and then again we use the product rule. First function multiplied by the derivative of the second function. Second function here is sine t square. The derivative of that will be cos t square multiplied by 2t plus the second function into the derivative of the first function. Let's simplify this. We'll get minus 2t square cos t squared plus sine t square. So that is the y component of acceleration. So let us collate and write down the acceleration vector. So the x component is, let us multiply the 2 with the entire bracket. So we'll get minus 4t square sine t square plus 2 cos t square. In the y component, let's multiply the minus 2 with the entire bracket. So we'll get minus 4t square cos t square minus 2 sine t square. and that is the acceleration vector. Now, going back to the question, we were supposed to show that the acceleration vector is never parallel to the position vector. So, the approach which we are going to take is we first will assume that acceleration is actually parallel to p. Let me repeat, we are going to assume that acceleration is parallel to the position vector of p. And on solving, if we get something which is illogical, then we can say that acceleration is not parallel to position vector. So this is like an indirect approach of solving this particular part. We already have identified the acceleration vector. Now let us assume that acceleration is parallel to the position vector. So let's write it down. Assumption. So this is the assumption which we are taking. Assumption is acceleration is parallel to the position vector. Now, whenever two vectors are parallel to each other, one vector is always written as the scalar multiple of another. So we can write a vector as k times r. So let's use that logic. Acceleration, which we found out, this entire thing will be equal to k times the position vector. And position vector is given in the question as sine t square and cos t square. So let's write that down. Sine t square and cos t square. So this is the assumption which we have done, that the acceleration is parallel to position vector, which eventually we have to reject or discard. So we have to, if you solve this, technically we should be able to get something illogical. And let's see, can we do that or not? Let us equate the x components on both the sides. So we'll get minus 4t square sine t square plus 2 cos t square. So that's the x component of acceleration. And on the right hand side, we'll get k times sine t square. Similarly, the y component of acceleration will be minus 4t square cos t square minus 2 sine t square. And on the right hand side, we can see k times cos t square is the y component. Now let us make k as the subject from these two equations. So from this particular equation, the first equation, if we make k as the subject, so this sine t square will go in the denominator of the left hand side. So let's do that. So sine t square, if we delete this, that will be taken in the denominator of the left hand side. And similarly, the cos t square, which is in the right hand side of the second equation, this cos t square will go in the denominator of the second expression. Now, since the values of k we have identified from both these equations, and then we can actually equate the two expressions. And if we equate the two expressions and try to simplify, let us try to do that. So the first equation, let's write again, minus 4t square sine t square plus 2 cos t square. This divided by sine t square equals to minus 4t square cos t square minus 2 times sine t square upon cos t square. So this is the entire expression after we equate the expressions for k. Now let's simplify further. We will cross multiply now. So the cos t square will get cross multiplied and the sine t square as well. So let us simplify. If you multiply cos t square with this entire bracket, what will we get? Let's see. Minus 4 times t square sine t square cos t square plus 2 times cos t square. There are two cos terms, so we will square that. That will be equal to minus 4 t square cos t square and sine t square minus 2 times sine t squared and squared. At this stage, you can see that there are two terms which are equal on both sides of these expressions. So which is this minus 4t square sine t square cos t square. So that term will get cancelled out from both these equations. And let us take the sine term on the left hand side. So we will get 2 times cos t squared whole squared plus 2 times sine t squared squared. And on the right hand side, we'll of course get a 0. Now on the left hand side, let us take 2 as common. And in the bracket, we'll get cos t squared squared plus sine t squared squared. And on the right hand side, we have a 0. Now we use the basic trigonometric identity that sine squared theta plus cos squared theta is actually 1. So on the left hand side, we'll get 2 into 1 equals to 0, which is 2 is equal to 0. Hence, we are able to get an expression which is absolutely absurd. It's illogical. Hence, the assumption which we had made in the first place, the assumption was this: acceleration is parallel to r vector. That assumption is clearly wrong. Hence, we can say that acceleration is never parallel to the position vector. And that's how we solve part B.